Good afternoon, everyone. Today we'll move on to our next topic, which is the introduction to structural analysis. Before we start, I'd like to point out that the subject or the course on structural analysis usually takes like 2 semesters or 1 semester if you really go through every methods for analyzing the structure. So since for us here we don't have much time for that, then we'll just um, discuss the basic principles, and then with regard to the methods we'll be using software analysis so that we can solve various kinds of structures. So it could be determinate structures or even indeterminate ones. Also, when we say structural analysis, it's actually a subject or a course that deals with the different methods of solving different kinds of structures. Okay, so it's all about methods, if we can put it that way. The main goal of structural analysis is actually to size up the member so that that member can safely and ideally um, be sized up economically. Okay, so for example, we have a structure here. Okay, so since the structure are subjected to various external loads, then each structural member shall be able to carry that uh, carry those loads or the results of that external loads, which are the stresses and the strains, or you can put it also as the internal loads and the deformations. Okay, so let's take for example the purlins on the roof. Okay, so the purlins on the roof has to carry the um, let's say that the dead weight of the purlins itself, and then the dead plus the dead weight of the roofing sheets. And if there are, let's say, there are wind loadings, significant wind loadings, then it will just um, will just include that in the analysis or the forces. Okay, so it's like this. This is your structure, and then it is subjected to external forces. So because of that, and since that structures are composed of individual structural members, like for example the purlins or the truss, the columns or the beams, then each of that structural components will be able to carry that external force. Okay, so when we say external force, we're also referring to the dead weight itself, or the dead weight of the structure itself. And later on, we'll discuss the different types of the structural loads. Okay, so this is your structure, and then there's an external force. The response of the structure is, we can classify it as in terms of stresses or internal loads. Internal loads, or we can say stresses if we're referring to the distribution of the internal loads. And the other one is the deformations. Or strains. Okay, so this is your external force. Then the goal is actually um, okay, the goal is to size up the member, size up the member to safely carry the loads. Okay, so we can say that's the nutshell of the structural analysis. So of course, when you are sizing up, then it means that um, given the loads, then we are to find out the dimensions, then that's a design problem. Or if we're already given the dimensions, then we can solve for the capacity of that section. Then that's going to be the analysis problem. Okay, so I think we'll write that down. So we have analysis, okay, analysis problem, meaning you're given the size, find the capacity. Okay, another type of problem is what we call the design. Okay, so design problem means that you're given the load, find the size. Okay, so since there are various types of structures and various types of structural members, and of course, um, another aspect is that structures are three-dimensional in nature. So the analysis would be complex if we don't use assumptions or idealizations. Okay, so it is really practical to make idealizations for a structural problem. Okay, so otherwise we cannot really we can't compute or we can't do analysis or design if we don't make idealizations. Okay, so one important thing is that, for example, as I've said that structures are three-dimensionals. So let's say a portal frame for storage housing. Okay, so this is your structure. It's a three-dimensional, but we can analyze the, let's say we have the purlins here. So we can analyze purlins as two-dimensional, or let's say one-dimensional. So that simplifies the problem. So it's something like we are isolating these purlins and analyze it as maybe like this, something like a beam. And then if you notice that purlins rest on this rafter of the frame, then we can also idealize the supports. So let's say, for, I mean, just an example, we'll use a pin roller support, or if you want, you can go for fixed support, and then we'll analyze the loadings. Okay, so that's one structural member. Can also be, I mean, you can also use continuous beams. So later on we'll discuss that in details. Okay, and then the purlins, I mean the portal frames, then you can also analyze it like as a 2D structure. Okay, so for example, that's our idealization. Then probably we can use maybe pin support, and then we'll make internal hinge. So something like that. We'll expose the loadings so that we can solve for the support reactions. Okay, so the point here is, even though that our structure is in three dimensions, we can convert it um, into two-dimensional problems, so making our lives or our solutions easier. Okay, so before that, also I'd like also to point out that when we're dealing with analysis of the structure, don't forget that we are bound by the provisions of the codes and also standards. I mean, from the loading side, especially. So we have to follow this. And I've already discussed the different codes and standards related to building construction or building designs in our lecture 1. Okay, so that's the overview. We'll detail now the idealizations of the structural members. Okay, so structural members, so we can classify the structural members in terms of skeletal elements and spatial elements. Okay, so the definition of a skeletal element is that the length is way greater than the other dimensions. Okay, so meaning that, for example, if this is our structural member and we have this cross section and then we have the length. Okay, so the length is way greater than our let's say thickness or width, may B, and then the thickness, or T. So the length is way greater than our width and thickness. For spatial elements, basically it's just small thickness as compared to the other dimensions. Okay, so example is the roofing sheet or wall or slabs wherein the thickness, you notice that this thickness is way smaller than the other dimensions. So let's say this is our width and then this is our length, for example. So the thickness is smaller than width and length. Okay, so for our skeletal elements, we have skeletal elements. We can further classify that as one-dimensional, or two-dimensionals. So example of a one-dimensional structural member, examples are axial members such as columns or struts. Okay, axial members, beams and other flexural members, and then others, many others. Okay, for this, the two-dimensional structural elements are, for example, trusses, frames, okay, trusses, frames, and arcs. Okay, something like that, arcs, cables. Okay, so let's discuss in detail axial members. So axial members, if you recall in the subject of strength of materials, then it's something like the different kinds of loading a material or a structure. Okay, so axial members are members subjected to either compression or tension. Okay, so for example, these are loading, so that's compression, or it can also be compression tension. So for compressions, the most common ones are columns, although other terms like, for example, struts or ties, or what else, tension bars. Okay, so tension bars, that's for tension loadings. Okay, so that's the example of one-dimensional beams. So for beams, it's a structural member subjected to flexural loadings. So when we say flexural loadings, it's it's the loadings that's perpendicular to the longitudinal axis of the member. So for example, this is our longitudinal axis. So you see that this loading is perpendicular to this center line. So whereas here in actual loadings, the loadings are parallel the to the center lines. Okay, so for beams, we have many terms like example, the beam itself, the general term like roof beam, for example, roof beam or floor beams. So those are example of flexural members. What else? Roof beam, floor beams, purlins. Okay, purlins are actually beams. Purlins, or probably geared, and the joist, the floor joist or roof joist in timber constructions. So those are the examples. Okay, and another one is the girder. So girder is also a term. It's actually a flexural member. So basically, the difference when we use girder and beam in one problem just means that girder is the largest beam, or we can say that the girder is where the other smaller beams rest on. So for example, this is our small beams. Okay, so these are our small beams, and then it rests on a larger beam. Okay, so the term would be, this one is it. This one will be the girder. A girder, and then this, let's say we can call it as floor joist, or just beams. Okay, so that's just about the terminologies. By the way, before I forget, another example for the actual members are the braces of the frame structures. So, for example, this is a frame, and then you can see braces here. So, these braces could be in either in tension or in compression. Okay, that's braces. Okay, so two-dimensionals. Two-dimensionals, we have trusses and frames. Okay, so for trusses, basically you'll see the trusses in roofing systems. Although it is also common in floor systems, like for example the steel joist, or something like open web steel joist. Instead of this triangular shape for the roof, then that's gonna be something like a flat truss. Okay, so that's the truss, and then the frame is, for example, the portal frame. Okay, so that's the portal frame. or square frame for multi-story buildings. Okay, so that's frame. Okay, so what's the difference between a truss and a frame? Okay, so the difference would lie on the how you would analyze the structure. So for the trusses, the analysis is actually we assume that the joints, okay, the joints of these connected members, okay, disconnected members, we assume a hinge, internal hinge, or let's say pin. Okay, we'll just use this internal hinge connection. Whereas here we analyze it as a rigid joint. Okay, so what's the difference? So here the internal hinge, it doesn't carry any moments. So we'll write it here, no moments. So meaning if this is the, let's say this is the joint of two members, means that the loadings would be or the load reactions, I mean not the load reactions, maybe the loadings at the joints would just be forces. There's no moment because we internal hinge actually allows rotation, so there's no moments here. Reaction, we can call it moment reactions, whereas in rigid joints we assume or we analyze it as there's actually moments here. Okay, so we have three support reactions. If you recall from your statics or circumponders, I think statics. Okay, so the support reactions, there are three support reactions, whereas for internal hinge there are only two. Okay, so that actually simplifies the problem. So meaning that we can analyze the truss because instead of having three unknown reactions here, if we analyze the truss like a rigid joint, then it's gonna be highly indeterminate. But since we assume that it's an internal hinge, then we can simplify the calculations. Okay, so now take note that in reality, the joint is actually, it's not a pin. It's not a pin joint. It's actually welded, and sometimes there's a gusset plate that's that that helps, or let's say that allows the connection of let's say bolted connections or welded connections. At least it can provide a larger weld length, for example. So that's actually a rigid joint. Then, it is commonly accepted that the analysis of truss, we can use an assumption that the connections are internally internal hinge. Okay. Also, another one is that the loadings. So loadings in the truss, we assume loadings. We assume loadings at the joint only. So we don't put loadings on along the member length. Okay, so it's just on the joint, along the joints. Whereas for frames, we can actually use distributed loadings along the member length. Okay, so if you notice that flexural loadings actually induces or produces moments in shear, but the assumption for truss analysis, we use only joint loads, so that also makes simplification the analysis. It means that the member itself only carries axial loadings, whereas the member here carries, it can carry shear, shear moment, and sometimes it carries axials, whereas here only carries axial loads. Okay, so the question now is, if we only assume a loaded joint, then what about the distribution of the purlins. Okay, so we say that there's purlins here, and what if the joint is at this point? Okay, so it's not directly at the bottom of the purlin. So let's say here. Okay, so in that case, the analysis would be we have, or we can idealize it like a force distribution, but since we're only loading at the joint, then we're going to take the tributary width. So example, half of this, so the half of the distance of this length, then all the loadings within this width. Now we can simplify it to let's say one loadings only, a single load. Okay, so that's how it's going to be analyzed. Okay, so next we'll move on to what else? Spatial elements. Spatial elements. Oh, sorry. Other structural elements for 2 dimensions are arcs and cables, but we'll not discuss it here. It's uh, it's included in our lecture handouts, but we're not gonna discuss it here. Okay, so spatial elements we have plates and shells. Okay, so plates we can further classify as, for example, the walls and the slabs. So, for example, this is the flooring. Then usually slab. That's a slab. The wall would be this part. Okay, so the loadings of the slab would be flexural loadings as well. Okay, for the shells, actually, the characteristic of the shell is that instead of a straight, let's say, straight plates or straight walls, it's actually having a curve, say a hyperstructure, for example. So it's a curved structure. Okay, another example is a cylindrical shell. So a culvert, for example. So that's cylindrical shell or a tank. Okay, so for us here, well, the common structural members that we'll encounter in this course would be the beams, columns. Wait, let's say beams or girders, columns, trusses, frames, and although we use hoop structure for the greenhouse, but will not cover that much here. Okay, so we'll continue our discussion in the next video. See you in the next video.